So, we have looked till now on certain basic definitions of compressible flow and Mach number and speed of sound, and then looked at thermodynamics because it is integral to the description of gas dynamics. So, let us look at a few numericals so as to familiarize with these concepts and how to quantitatively look at these numbers. So, in this example 1, so a person on ground sights an aircraft right above his head flying at uniform altitude of 3 kilometers, but hears its sound only when the aircraft is at a distance of 6 kilometer in his line of sight. Calculate the Mach angle and Mach number of the aircraft, estimate the time for which he was in zone of silence. So, it is always useful to sort of look at it in a diagrammatic fashion. Okay, so now let us look at what has been given here. It is good to represent it diagrammatically. So, if you consider a person is standing here and he observes an aircraft that is going right above his head, but at that time he did not hear anything. Okay, but along his line of sight, so this is his line of sight, and when the distance is 6 kilometers, so this is 3 kilometer, he is able to observe the sound, or he is able to hear the sound of this aircraft. So, that means at that point of time the Mach wave just passed over that particular point where the person was standing. So, that means that this is the Mach angle over here mu, and then for we know that the Mach angle is related to Mach number, sin mu is 1 by m. Okay. So, directly from the trigonometric relation over here, sin nu is 3 by 6 1 by m, or you can get that Mach number is 2.0. Okay. Now, if you consider this, then the second point over here is that estimate the time for which he was in the zone of silence. Okay, so that is the second part. To calculate the zone of silence, we need to find out the time. Now, the distance that is actually moved on ground during this time is this one, which is x. So, by the aircraft. So, the time taken is during this time is t is basically x by the velocity of the aircraft. Now, the velocity can be calculated by the definition of Mach number itself. So, Mach number is v by a. So, you get v is m multiplied by the speed of sound. You need to know the speed of sound, and the speed of sound is given here 328.58. So, you get the velocity from that. Velocity is 657.16 meter per second. So, now you need to find this x. You can do it by trigonometric relations. Okay. So, you know the angle here, angle is if you know sin is 1 by 2, that means angle is 30 degrees, and then you can calculate x. So, x is 5.1962 kilometers here. So, then time then is t will be 5.1962 into 10 power 3 divided by the velocity 657.16 which is you get about 7.91 seconds. Okay. So, this is related to the concept of Mach angles and the concept that in supersonic flows you cannot know that an object is passing right at the moment it is sighted or it is at that position, but at a later time when the Mach wave passes over that particular point. So, there are definite directions of propagation of information in a supersonic flow. So, this is the concept that is important over here. Now, let us look at the second example, which is related to thermodynamics. Okay. So, here the question is, air is expanded in an insulated cylinder equipped with a frictionless piston. The initial temperature of air is 1400 Kelvin. The original volume is 1/10 of the final volume. So, if I take two states, say 1 and 2, state 1 and state 2, initial temperature is given, it is T1 is 1400 Kelvin and the original volume is 1/10 of final volume. So, what is given is V1 by V2 is 1/10 the final volume. Calculate the pressure ratio and change in temperature. So, how do we go about doing this? So, this involves the concepts of the ideal gas and also the concept that it is an insulated cylinder equipped with the frictionless piston. Now, this is the case of an adiabatic flow without any friction or any reversibilities. So, any irreversibility. So, it is a reversible adiabatic process, and that kind of a process is the isentropic process. So, it is an isentropic process that is given over here. So, we know the ratio of the volumes. So, the corresponding thing is P V power gamma is constant. This is the equation that you would use here. So, what you would get is P1. So, we need to find out the ratio P1 by P2 is actually V2 by V1 whole power gamma. This is air, for air gamma is 1.4 and V2 by V1 is 10. So, because V1 by V2 is, so you get P1 by P2 is 10 power gamma, which is 10 power 4, this is 25.12. Okay. So, the pressure in the initial case is higher and it is 25.12 times the pressure at the final point. Okay. So, now the second question is that calculate the change in temperature. What is change in temperature? That is, you need to know what is delta T, which is T2 minus T1. That if I divide this by T1, I will get delta T by T1 is T2 by T1 minus 1. Now, we know the process that is happening over here. It is an isentropic process, and the isentropic process, we know the relationships between the different quantities. So, now also you can use the PV is equal to RT, which is the ideal gas law, and That means here you can use P2 V2 by P1 V1 minus 1, because R is a constant in the case. So, you can use this. So, this you can write it in terms of so you have already found out what is P1 by P2 and V1 by V2. So, P2 V2 by P1 V1 minus 1. So, this can be written as 1. So, V2 by V1 is 10 and P1 by P2 is 25.12 minus 1. Okay. So, this comes out to be a negative number. So, and this gets multiplied by the T1, which is, so this number is 1400 Kelvin. So, you get a delta T, that is change in temperature, is equal to minus 842.67 Kelvin. Okay. So, we have addressed the two things. So, the two important concepts that were used here is the fact that the process involving an adiabatic reversible process is an isentropic process. Using that we were able to calculate the pressure ratio given the volume ratios, okay, and the concept of the ideal gas law to calculate the change in temperature. Okay. So, this is an example where these two concepts were involved. Now, let us go to the third numerical example. So, in this air is allowed to expand from an initial state A, where Pa is equal to 0.068 into 10 power 5 pascals, and temperature is 333 Kelvin, to a state B, where pressure at B as 1.034 into 10 power 5 pascals, and temperature at B is 305 Kelvin. Now, calculate the change in specific entropy of air in an isobaric process from A to some intermediate state C, followed by an isochoric process from C to B. So, the state movement from state A to B is achieved via an intermediate state C, and the relationship is that from A it goes to state C, which is through an isobaric process, and then from C it is followed by an isochoric change, okay, isochoric process. Okay. So, this is the point. So, let us and then represent these processes on a PV and TS diagrams. Okay. So, quickly if we look at the PV diagram, because the pressure and so if you look at that, so this is PV diagram. So, V is given, and we know that temperature actually increases when you go in this direction. So, T increases. So, you can draw two constant temperature isotherms or constant temperature. So, this can be the lower temperature, which is Tb, and this is Ta, and it is known that this is say point A, which is at higher pressure, and this is at point B, which is at lower pressure. Okay. And so, the isochoric process is here, it is a vertical line, and the isobaric process is a horizontal line passing through A. So, immediately from this description we see that C is lying here, which is, that means it has an increase in temperature. So, here as it goes from this state to this state, there is an increase in temperature, and further followed by a reduction in temperature and pressure. So, this is the advantage of using these charts that help us immediately without qualitatively understanding the flow field or the thermodynamic processes. So, now if we do calculate it numerically, then you can do it. The concepts involved here are what is an isobaric process, what is an isochoric process. So, since you know that Pb equal to this is known, Pc equal to Pa and Vc equal to Vb. Okay. Now, when both pressure and temperature are given, we can calculate Va is using the ideal gas relation, Pv is equal to RT. So, Va is RT by P. You can do the substitutions here. This is air, so you can take that, and 333 divided by 2.068 10 power 5, which is equal to 0.462 okay, meter cube per kg. Okay. So, similarly Vb you can calculate, this will be 287,305 divided by pressure is 1.034 10 power 5, and this turns out to be 0.847 meter cube per kg. So, so directly we know Vc is equal to Vb. So, we know the value for Vc here. So, we can calculate Tc can be calculated from here, that is it is Pc Vc by R, which is Pa Vb by R given the relations. So, here if you do plug in these numbers, you will get this is 610 Kelvin. This is about 610 Kelvin. Now, if you want to look at the entropy, then change in entropy from A to C, that is what you are interested in. So, this is an isobaric process. So, delta S you can use the relation Cp log of Tc by Ta minus R log of Pc by Pa, but Pc and Pa are the same. So, this term goes off, you directly get Cp, Cp is 1005 log of Tc by Ta, Tc is known here 610 by Ta, Ta is 333. So, this you should get a value close to 608 joules per kg Kelvin specific change, and change for the process from C to B, this is A to C. For this it is a isochoric process. So, you could use Cv log of Tb by Tc minus plus R log of Vb by Vc, and here it is an isochoric process. So, this goes off. So, you get you have to use the value of Cv, which is 1005 by gamma. Okay. So, this value if you plug it in, then you will get this as a negative number, which is minus 497.33 joules per kg Kelvin. So, you can calculate the net change of entropy, and that is you have to add these two, next change in entropy, and you will get that delta S is from A to B is about 110.6 joules per kg Kelvin. To cross verify, you can always go back and just take, because entropy is going to be a state variable, you just have to pressures and temperatures. You can use this relation and cross check that you get, if you substitute TB and PB, then you should get the same number, same number that you get over here. Okay, to now represent this on a TS diagram. So, this is a TS diagram, and the constant pressure process is a curve. So, starting from a value over here, which is A, it is a curve which goes up to a value over here, because temperature increases, and then isochoric process has a slight higher slope. So, you come to a point here which has a slightly lower temperature, but you observe that as we have seen, delta S is positive. So, here this is pressure equal to constant, this is volume equal to constant. Okay. So, this particular example involves calculation of entropies, ideal gas laws, and the thermodynamic charts. So, I think this is a good sort of exercise to be familiar with these concepts, so that when we go on to do them in gas dynamics, you do not have to you become comfortable with these kind of computations. So, the next class we will start looking at fluid flow equations.